we're actually going to understand the feature information. And of course, understanding feature information, we'll be able to understand the grammar all about. Okay, so the essence of score function in real life application, lies in its ability to enable accurate parameter estimation. Okay, and that form the foundation for decision making, predictions and optimization across diverse fields and industry. So which means if we're able to leverage the score function, okay, practitioners will be able to extract insight from data. And when they extract insight from data, okay, that will improve processes and they will be able to make informed decisions to address complex challenges and achieve desired outcome. Okay, so I'm going to walk you through, the mathematical way of presenting score function. Okay, now the score function is actually significance, just like what I said. And of course, I'm also going to show you that the expectation of a score function, okay, is equal to 0. Okay, because the significance of the expected value of score function or B0, actually lies in its connection to the properties of estimator, okay, like efficiency of estimator and asymptotic, or behavior of estimator, okay. But let me first, I'm actually going to stop my share now, okay, and I'm going to present to you. Okay, I'm going to present to you, okay, score function. Okay, like I said, a score function in a random variable, mathematically speaking, is actually going to be, uh, you know, change, okay, in the, in the natural log, okay, of a given probability of distribution. Okay, so that is a score function. Now, if this is a score function is a random variable, okay, the expected value of it, okay, we want to show that is going to be equal to 0 because I told you the other time, when the expectation of a score function equal to 0, okay, it actually mean that, it does not provide any systematic bias in estimating the parameter. And if that's actually happen, it means, in our estimation, we're not going to underestimate, we're not also going to overestimate. Okay, the implication of the expected value of a score function being 0 is very, very crucial in consistency of a parameter. Okay, when you want to talk about the convergence of estimator to the true value of a parameter in probability, when you work with a sufficiently large sample, that is going to happen when the expected value of a score function equal to 0. Okay, and let me tell you this. I'm going to show you mathematically now. Okay, I'm actually seeing a score function to be a continuous random variable, and I want to find the expectation of x. Okay, so it's going to be expectation of that guy equal. So, the integral. So that guy that I call the random variable, okay, then I'm actually going to have the f of s given theta dx. Okay, so this guy is a random variable. This is similar in statistics where we do expected value of x and where we have x, you know, f of that ds. Okay, so it's similar to that. Okay, so when we have that now, what we want to do, okay, the expectation of that is going to be, now we want to focus on d theta, lane of f of s theta. Okay, so the d theta that can actually be written as d theta, okay, f of s given theta divided by f of s given theta. Okay, if you perform a derivative of that one, then multiply by f of s given theta, okay, dx. Okay, so when you do that, this is going to cancel that. Okay, situation, when that cancel that, so what is going to happen? What are you going to be left with? Okay, you actually gonna bring this guy out, okay, integral f of s of this dx, okay? So what is the total area under a curve? It's gonna be one, right? Integral of a valid probability distribution is gonna be one. So I'm actually gonna have the theta of one. And when I differentiate that, it's gonna be zero. Okay, so what have we done now? So we've been able to establish the fact that expected value of a score function equal to zero. Okay, I told you the other time. Okay, expected value of a score function equal to zero, okay, has a significant implication in the research world. Okay, and what that is telling us is that the estimation of parameter is not going to bring in any systematical bias. Okay, so any systematical bias that will affect our estimation. Okay, and with that, we're actually going to have a precise statistical model. Okay, so I've been able to show that. So the next thing we can talk about now, okay, is if I want to do expectation of S squared. Okay, want to do expectation of a square, like what is the expectation of a square of, expectation of a square of a score function. Okay, and I'm actually going to say the expectation of a square of that is the same thing as Fisher information. Okay, Fisher information. Okay, now the Fisher information is expected value of the square of x. Okay, so let's take a look at this. From the knowledge of statistical theory, the variance of x is expected value of s squared minus expected value of x or squared, right? Okay, so that implies the variance of s is going to be equal to the variance of s is going to be equal to that's plus expectation of s all squared. And of course, I told you the other time, expectation of s, this coefficient equal to zero. So which is going to tell you this is going to be a variance of x. Okay, and that is going to be expectation into, okay, d theta ln f of x theta are going to be squared. Okay, if you take a look at that now, this is what we call Fisher information, okay, for one sample, for sample size one. Okay, so what do I mean by Fisher information? The Fisher information is going to tell us the amount of information that is contained in the data. Okay, the amount of information the data has about the value of a parameter. So we believe that the more the Fisher information, the more the Fisher information, the more the data is informative. Okay, we actually want our data to possess more relevant information about the parameter of interest. Okay, so the larger the Fisher information, then the more is actually informative, just like what I said. And let me tell you this, which means the larger the sensitivity, okay, the larger sensitivity of f of x given theta to changes in theta, then the larger should be the information that we actually are talking about. Okay, so take a look at what we have now. Like I said, this is for one for one data point, like s equal to 1. Okay, so when we have for two data point, of course, the Fisher information is going to be additive. Okay, so what I want to do right now, okay, is writing the Fisher information, okay, for sample size 1, and also, for sample size 1, okay, I'm actually going to say, for sample size 1, the score function is the theta ln f of x theta. Okay, situation where I actually, at time I could have as many, multi-parameter situation. Okay, I'm actually going to have this guy now. Okay, now if I actually have that guy now, okay, the information now, okay, which is actually this, okay, expectation of s squared, just like what I said, is going to be d the theta ln, okay, f of s given theta all squared, like I said, okay, but for n sample, for sample size n now, for sample size, okay, n, okay, the Fisher information is actually going to be n expectation, okay, d theta ln f of s given theta, because the Fisher information is additive, the information carried by combined law, or maybe f of x1 comma s2 up to Sn, okay, given theta, should be the sum of the carried information, the Fisher information for each. Okay, and that was why information is actually additive, and we're also going to say information should be insensitive to the sign of the change in theta, and of course information should be deterministic or quantity. Okay, so now that we have actually discussed the score function, the expected value of score function equal to 0, and expected value of the square of score function will give us a Fisher information, which is the amount of information, okay, that carries about the values of parameter. And the more the Fisher information, of course, the more the sensitivity of the more the information, because the score function in general is actually talking about the change in the underlying probability distribution when the parameter changes. So the larger the sensitivity of f of s given theta to changes in theta, the larger the information. Okay, so this is going to prepare us a ground for Cramer or lower bound. Okay, watch that in the next video.